Okay, so we I think we only have 3 classes left. Um, so let me actually first talk about the schedule for the rest of the semester. Uh, so I believe we have um, so today is the 29th, okay, and then we have um, May 6th, oh May 4th, um, 29th, May 4th. Okay, so I'm not setting up the pane correctly. So May 4th is next one, and May 6th. Uh, now, technically, we still have, you know, May 11th. May 11th is actually it's in the final exam period. So it's technically May 6th and May 11th is in the final exam, you know, period. So the last day for class is May 5th. So we only have 2 classes left plus 2 flexible time we can use during the final exam time. Um, I hope that I can complete the talk on May 4th. So then we can actually leave May 6th kind of flexible. Um, so the plan is to have the final exam on the day of May 11th. Now, just like the previous test, um, I'm not gonna actually stick with one particular time. I'm gonna give you some flexibility. So you can again you can start the test. Let's say you can start the test from. I can even actually set it like a 9:30 a.m. to probably to the end of the day. Okay. So okay, just like the other tests. Okay, so that's for the final. Now final gonna be a little cumulative, but we mainly going to focus on the last 2 chapters. We're going to mainly focus on uh, the file system and I/O. I think we actually also going to, you know, cover some of the memory management because I think the last section of the memory management was not covered in the previous test. So it's probably like chapter 8 and chapter 9, the son of the chapter 7, I believe, part of the chapter 7. So, so this is just like a general, schedule. So the final going to be scheduled on May 11th. So for May 6th, I may not schedule a class, but I will make myself available at the time. So if you have any questions during the class time, so you can log in and you can chat with me. Uh, but I'm not going to cover any class. So we only have 2 left. Okay, today and next Tuesday. Okay, so just stay tuned. So, you have any questions? I think I basically published all the tests on the Zybooks. Um, so you can actually work on the Zybooks. And as I say, if you miss some of the assignment, um, you can just let me know. So you can still get partial credit for the if you miss the due date. Um, that's always my class. Uh, that's always the case for my class. Okay, so if you don't have any question, let me. I'm gonna actually continue with the talk. So last time we discussed about um, how you're gonna allocate the file in the hard disk space. Okay, so in the hard disk space, all the data are gonna be the files gonna be actually stored as blocks. So this is very similar to, not exactly the same, but very similar to the memory management when we use the page, right? When you use paging, so you basically divide the any actually program into a small block called pages. So you measure the program in terms of the number of pages. Now this is very similar. Now for the file, for any file, when you try to store the file in the hard disk or in any you know physical medium, so the file is going to be also divided into blocks, and then we store each piece of block into the physical block in the hard disk. So so now so the disk is actually divided into blocks, and then the way that you save the file going to be different. There are a couple of different ways for the disk block allocation. Uh, Now we talked about contiguous block allocation last time. So in the contiguous block allocation, so when you actually store a file, which is actually takes like a 4 blocks, for example, and then we need to find in the hard disk a contiguous actually hard disk space, which has actually 4 block. Okay, so in this particular case, if we have a 4 blocks, and then we find out, you know, the physical block 14, 15, 16, 17 is available. So we actually put the file in these 4 blocks. They're actually in the nearby location, in the in the consecutive location. Now, in case, so you want to expand the file. So for example, if you doing the homework, you want to add another problem, add another answers, so the file size is going to expand. So this file going to actually need one more block or multiple blocks. And then in this case, you need to check whether there's actually additional 3 blocks, nearby. So after the actually 17, you find out, oh, 18 is available. So then you can actually expand, you know, ex, expand the file size to 5 blocks. Now, if you continue to expand, then you need to actually find another chunk of hard disk space with enough blocks. So that's something we just discussed last time. So initially we discussed the contiguous allocation, and then we talked about the linked allocation. Linked allocation is very flexible, but unfortunately it's very slow because you don't care where the next block is going to be. So then you may actually have a situation that you try to save a file into the hard disk, and this file is divided into like a couple of blocks, like 100 blocks, and then these 100 blocks are distributed all over the places in the hard disk. So when we try to actually open the file, then when you try to search search a block or search a data, then you have to actually follow this linked list one after another. So it's a slow, and also you cannot perform direct access because you don't know which block is in which location. You basically follow the link of the previous block, and then you find the next block. You find the next block. That's why it's not really that, attractive, you know, acceptable, that you can actually effectively manipulate the hard disk space. Okay, so you don't care, whether this is an isolated block or not, because you can always point, to that block and store the data in that block. So, so these are the cons of these linked allocations: slow, and inability to perform direct access, and decrease the reliability of the disk. Okay. Now, if you have a file that's scattered all over the places, it's actually a recipe for making mistake. If one of the link is lost, one of the link is, for example, a portion of the hard disk space is messed up. Okay, so you cannot read that particular space block, and then you lost all the follow-up files. This is actually sometimes it's a serious problem. So for example, if you have a hard disk blocks, if you know the files are all nearby, okay, now if one of the block is messed up, then okay, so this part I cannot read this block anymore for whatever reason, because this particular block is, there's something wrong. It happens, right? If you actually store the in a CD or DVD, it's possible that the particular portion of the DVD is scratched. So you suddenly there's a big dent or scratch in that particular location. So this piece of the data stored in this piece of location is messed up. Now, if you use the contiguous allocation, then you're going to lose that part of the data, but you may be able to recover the remaining part. So you can actually at least get the other piece of data correctly. Now, if you use a linked list, now this piece is actually linked to another one, and then this piece linked to another one, and that piece linked to another one, and that piece linked to another one. So now, if this is actually messed up, then you lost the follow-up blocks, because follow-up blocks rely on the information in this block. Okay. So this is actually definitely a big disadvantage for the linked allocation. Now, in Microsoft or other computer actually system, they actually sometimes people actually use some kind of a tool called defragmentation. They try to push all the blocks for the same files together. Okay, so this is actually linked list. And the last case is the clustered allocation. So the clustered allocation basically, it's kind of a hybrid between linked, contiguous allocation and the linked allocation. So they try to, if there are a cluster of blocks that are available, then you try to actually store all the files, in this cluster, so they're nearby, they're contiguous. But once you reach the end, so then the next block is not available, that's not the end of the world, because then you use the link to point to the next cluster. Okay. So the cluster basically solves some of the advantage of, some of the disadvantage of the contiguous allocation, and also solves some of the disadvantage of the linked allocation. But still, now you cannot perform any direct access because you use the link. So you cannot directly jump to a particular block, because you never know which block is actually pointed to by the previous block, right? So that's the clustered. Now, a more actually popular approach is called the file allocation table, which was used and may still be used and initially by the Microsoft operating system. It's called a FAT, file allocation table. It's an array where each entry corresponds to a disk block. So, it has a cost. You're going to create a table which stores the array of something very similar to the index, but we don't call it the index. So the FAT, the file allocation table, keeps track of which disk block belongs to a file by linking the blocks in a chain of indexes. Okay. So the FAT information is also stored in the file control block. It's kind of indexed the first file blocks. It just contains the, and then which in turn contains the index of the next blocks. Okay, so the FAT table is actually stored in the FCB. Now here's how we're going to illustrate the file allocation table. Okay, so here's the actual disk blocks. This is the actual physical disk blocks, and this is the FAT table. Okay, so this table is stored in the, actually not the table, but table is stored somewhere, but the first block actually is stored in the file control block. So for example, if I store the files in the disk blocks, the first actual block is 7, let's say, or 14. Okay. And then the next one is 17. Okay. So instead of using linked list, so then you put the reference information at the end of the block and point to here. Now we use index table. Okay, it's called a FAT, file allocation table. So then the first block is stored in the physical location 14. So then that 14 information actually points to this index. So in the index table, so index 1, 2, 3, 0, 1, 2, 3, 4, 8, and then it is actually in the 14, actually it stores the next index, which is 17. Okay, so it's very similar to linked actual allocation, but that information actually, the link information is actually stored in the FAT. So then the 14 points to 17, 17 points to the 3, okay, 3 points to 9. So you don't actually physically point this one to each other. So if this piece is messed up, it's okay, because we don't rely on the information stored in that block. We actually, the link information is actually stored in the FAT. Okay, unless that information is messed up, then we're finished. Okay. So then each index is actually linked to the actual physical block. Okay. 14. But you know that the first actually block, for the actual file, you actually start from the block 14. So you don't have to follow the blocks in certain order. So you can actually, allocate your files in many different locations, and these locations are actually linked using the FAT table. So that's called a okay. And the other approach, it's now it's called indexed allocation. Now the indexed allocation, it's very straightforward. It's actually more like physically the file is actually saved in different blocks. Starting with the 14, then 17. Now, instead of using the fat allocation table, which link each of the block to the next block in the fat table, now they directly use these index table. Okay, so in the index table, they put all the the blocks for this particular file in the contiguous location in the index table, not physically close to each other, but in the index table they are close to each other. So the index table is more like a virtual contiguous allocation, and the fat table is more like a virtual linked allocation. Now, the link is actually not in the actual physical location. It's actually in the fat table. And in this case, it looks like contiguous, right? But it's not, So in this particular example, it's the same example. So we have the file occupies the block 14, 17, 3, 9. That's the order. Instead of let 14 point to 17, 17 point to 3, 3.9, then we order, put these blocks in the index table. We put this block in the nearby location. Okay, in such an order. Okay, so in this case, the index table contains number of 4 blocks. So because the file takes 4 blocks, so you're gonna take 4 blocks. Okay. Now the access is pretty simple. If it doesn't matter now, in either case, whether you use a fat or indexed block allocation scheme, so it has nothing to do with the physical block, right? So if this physical block is messed up, okay, that particular location has a scratch, so this piece of data is lost, then you don't lose the information of any other block, because if this 14 is messed up, it's fine. The next one is 17, so you can just look at the 17, 3, 9. So this basically defines the the index table basic point to each of the blocks for the file. Now, one of the just like the contiguous allocation, which is not really that flexible, because what about if you're running out of space? Okay, so for example, if your file is basically use 4 blocks, 14, 17, 3, 9, so then in the index table, I'm gonna actually take 4 blocks, 0, 1, 2, 3, in each actually number corresponding to the block number, the actual block number. Now, what about if so then at the next table, I can, for the next actually a file, I can use 4, 5. So next file, I use 2 tables, and the 4 is, but this is corresponding to another file. Okay, so then 4 is point to 10, so then point to 10. Okay, 5 is point to 18, for example. Okay, but that's related to the other file. Okay, now what about if I want to increase the file size? For this first file, I currently use 4 blocks, but I want to increase the number of blocks into 6 blocks. So I just expand the file size. Now in that case, now you find out number 4 is used by another file. So it's not really flexible. So in this case, so you cannot expand. So that's the reason why using indexed allocation, sometimes you need to make sure, to leave some free location here. So make sure these two actual numbers 4 and 5, please do not use this to allocate the other file. So your next file gonna start with 4, 5, start with 6. Okay, so you leave that space free. So once you actually allocate another space, and if you say, okay, so I want to actually add another block, the next block after 9 is, for example, 10. So then I can actually point this to 10. So the next one is 18. So then your file can expand. Okay, so in this case, when you actually create the index table, so you should leave some space for each of the file in case each of the file going to expand. Okay, so that's the part that so make this indexed allocation a little less flexible, than the fat table, because in the fat table, you can freely just allocate this one in the fat table, right? So next time you just find out, oh, this one is not used, then you can actually. So and the last one over here is, so what is the last one? So 4 to 7, 17 to 3, 3 to 9. Oh, okay. So then I can point the 9 to 2, right? Okay, so I can use the space 2. Okay. But use indexed, it's very similar to the contiguous allocation, but not physically contiguous allocation, but it's contiguous in the index table. Okay. Now, one good thing about index table is, you can actually you can expand the index allocation using something called multi-level index block. Okay. So here's the diagram. So in the file control block, using index table, remember in the fat table, you basically just store the information of the first block, right? If the first block is 17, you store the first block if you use fat. And then the first block 17, actually, then you can, based on this 17, then you go to the fat table, and then the 17, actually, block 70 contains the information of the next block. Okay. Block 17 contains the information of the next block. So you can actually do this. But indexed is not. So if you adopt the index allocation, then in the FCB table, the typical approach is that you can actually store the first 10 block in the actually FCB table, like block 0 to block 9. These information actually stored in the FCB table. Okay, and then if the file contains more than 10 blocks, and then you actually start to build a index table, and that's the level 1 index table. Okay, this is actually level 1 index table. So the level 1 index table contains 128 blocks. So now your file control block contains 10 blocks, right? So basically, so your file control block contains 10 blocks. And your level 1 contains 128. So 10 plus 128, that's 138. So for the first 138 blocks, then you can, you can actually store in either file control block and the first level, level 1, indexed actually. So the level in 1 index actually contains block 10 to 137. Okay, so the block 0, you can have like 14. Next one is 20. The block 10, block 9, which is the 10th block, is like 100, something like this. Now, if you have more, then you're gonna actually, so the next one basically just point to the first actual level, the level 1 block. Now, if your file is extremely big, you have more than actually 138 blocks, then you're gonna actually build a second level index. Okay. Now the second level, it's actually, so basically in the first level, you still have actually total of 128. So that's block 137. Then you have a 138, 139, all the way to what is 138 plus 128. And then in each of the block, you're gonna point to another block, another 128 block, 128. So each actually block in the level 1 contains, it's actually point to another 128 blocks. So that's why if your file is very small, smaller than 10 blocks, then the access to the file is going to be very quick because every information is stored in the FCB. Now, if your file is a little bit bigger, but smaller than 138 blocks, then you can actually finish the accessing each of the block by just look at the what level 1 index. Now, if your file is extremely big, then you need to use level 2. So this is actually a kind of arrangement that it's kind of a trade-off. So you can actually make a small file access very quick, and you can make a big file access a little longer. That's called, basically they use multi-level index. Okay. So the second level index block contains total of 108 because that's 108. Now each small block contains the information of another 108 blocks. So you have a 108 total, each corresponding to a 108, 108. So you have a 108 times 108. Okay. So that's a total of 16,384 blocks. Now you can continue that trend. You can have a third level, okay, index structure. So that's even crazier. So that's the idea of index block. Okay. So that's the different, the allocations for the file blocks. Okay. Now, the last thing we're going to talk about is how the operating system file system manage the free space. Okay. So which space is free, which space is not? Okay. So to managing the free space is relatively straightforward. Okay. So basically, the operating system file system maintains a kind of table. It's called bitmap table. Bitmap. Okay. So it's kind of like a data structure, but it looks like it's actually a table. Okay. So the bitmap basically tells you, which block in the hard disk is free, which block is used. But it does not provide the details like which block. It only tells which block is used, but it does not tell you how the block is used, which file is stored in that block. That requires the previous topics, right? The block allocation. Then you need to check if you use the FAT table, the file allocation table, or if you use the index or whatever the method you use, and you can actually track which block is used by whom. But the free actually space management is basically just for the file manager to see the file system to have the overall picture of the hard disk usage. Okay, so that bitmap table basically, contains the number of bits. Each bit corresponding to a block. So let's say this is hard disk space. Okay, now block 0, block 1 are used, and the block 10, block 11, block 12 are used. Okay, so the number of bits equals the number of blocks in the physical disk space. Okay, so suppose each block takes 512 bytes. So that's the size of the block. Okay, and then that's the size of the block. That's the size of the block. Okay, now each 1 bit corresponding to a block. So if this first block 0 is used, so then in the bitmap, the first bit is set to 1, and the second bit is set to 1 because these first two blocks are used. Now, if the bit actually is set to 0, that means these bits in the hard disk are free. These are free. Okay. Now, so these 3 are occupied. Okay. And then the next bits are free. So each bit corresponding to a block, and the value of the bits basically shows whether the block is used or not. If the value is 1, that means the block is used. If the value is 0, that means the block is not used. Now, what's the advantage of this bitmap? So in terms of the free space management, this is very straightforward, right? But however, that bitmap table also takes some memory space. But the memory space it takes is minimal. Okay. So what's the overhead for the bitmap? Because every 512 bytes, you just use 1 bit to manage it. Okay. Every 512 bytes, which is 1 block, you use only 1 bit to manage it. That bit value is 1, then that means the block is used. If it's 0, that means the block is free. Okay. It's that simple, right? Now, what's the overhead for the bitmap? What's the overhead for the bitmap? Now, what is 512 bytes? How many bits for 512 bytes?
4096.
Oh, you calculated it, right? So it's actually 512 times 8, right? Because 1 byte equals 8 bits. So 512 bytes equals 512 times 8. That's 4,000. What's the number? 4,000?
4096.
Okay, 96. That's the number of bit. So that means for every 4,096 bits, you just need 1 bit to manage it. Okay. So that's the reason why the overhead is just 1 out of 4,096. Okay. So they put 100 because they use a percentage. So that's out of 100. But that's this. So it's at 0. Okay. That's acceptable, right? We don't just need actually 0.024% of the space to manage each, no, the total space. And you only actually use that much. So for all the memories, the disk space, you only use a small portion just to manage the rest of the space. That's really, it's minimal, nothing. It's okay. Compare with size it manages. This space that they used by bitmap is nothing, Okay. So this basically, we actually basically wrap up all the topics in the, in the hard, in the hard disk management, the file system. Okay. Any questions on this? So please actually check the Zai book and then make sure you're doing the homework exercises in the chapter 8, which is the file system. Okay. The last topic we're going to talk about is the I/O, input output. Now, this is also one important part of the operating system. So the operating system is just a piece of software that manages the processes, manages the memory, manages the file system, and also manages the input and the output devices. You can actually do a lot of work using computer system, but eventually, when you actually run a computer system, you need to actually import a value. You need to actually, trigger a program, right? And then once you actually run the program gonna actually generate the output. So the output should be either displayed on a monitor, or you need to print out using a printer, right? Or if you play the music, the output is actually just a music, a voice. Okay. Now, if you play the video, the output is just actually the movie. So you have to actually use the input-output device to show your input data and show your result. Okay. So this is very important. So this is also important part of the operating system. Okay. Now, when we talk about the input-output device, it sounds like we're talking about hardware, right? Yes, the input and output, they are hardware. hardware devices. Like one of the import device, can you list any of the import device? What are the import devices?
Keyboard.
Keyboard. Okay, keyboard is an import device. Okay. Your mouse, right? You can click the mouse and then you can trigger something. So that's also an import device. In the touch screen, it's more complicated. Your hand, touch the screen. That's also so touch screen. Now, in automated system, like the computer system installed in your air conditioning, in most of the automated machine, it is a computer, but you don't manually actually import the data, but you use the sensor to collect the data. So, for example, like air conditioning, in your control. So normally there's a sensor. The sensor gonna actually, the temperature sensor gonna actually basically monitor the temperature outside and find out. In your program, you set up the line says, oh, if the temperature is actually raised above like 70 degree Fahrenheit, then you start to execute the program and trigger the air conditioning to run. Okay, so in that case, you use a sensor, right? Your sensors could be also import devices. Now your output devices actually, also you have a lot of different output devices. Okay, what are they? Monitor, right? So monitor is actually kind of a tricky because in the touch screen, monitor could be used as input, but monitor also definitely going to be used as an output, right? So the touch screen monitor is also and also an input and output. Okay, and printer. If you connect the printer to your computer system, then you need and a speaker. Okay, lots of different output devices. Now, however, even though the import output devices are hardware devices, however, to trigger these devices, you need a software. So that's the reason why there's certain place that there's a border between the hardware and the software, because the software controls the hardware. So for example, you want to print, then you just click the print command in your Microsoft Word. So then how this actually printing command happens? And then, so between the actual output devices, you have something called device controller. Okay, so here's a typical computer system. Okay, now here's your CPU, and all these devices memory, and here's your hard disk, and here is your whatever keyboard or mouse. Now these devices are all connected to the bus, the system bus. So they connected to system bus. But before they connect to system bus, there's a piece of hardware. It's called a device controller. So hard disk, there's a hard disk controller. Okay. So, and for the keyboard, it used to have a keyboard controller, but now most of the keyboard mouse, they use the USB controller, right? USB controller. USB controller. Okay. So these are all connected to the So a controller is an electronic circuit capable of operating specific I/O device using binary signals. Okay. So now to control the device, um, so in the interface to the device controller is a set of hardware registers and the flags. Okay. Okay. So now sometimes in some of the operating system book, if you look at some of the operating system definition, they're gonna view hardware registers and the flags. They are part of the controller. But some like this in this side book, they actually view this, you know, registers are actually some kind of interface to the device controller. So it's not like it's kind of like a gray area. Okay. So some people think that the registers, the buffers, and in the controller is a part of the controller, but sometimes they call it it's just the interface with the controller. Okay. So now these device controller gonna be communicated with a piece of software called a device driver. So device driver is a piece of software. Okay. So this piece of software going to be loaded into the computer memory. When you actually start the computer system, this device driver going to be loaded as a part of the operating system. Okay. So all these device driver is housed in the memory. Okay. Now each of the device driver controls the device. How the device driver controls the device? The device driver controls the device by set up the registers, over here. And these registers are going to be used by the device driver. So device driver put the data into the registers. And then the controller also read the registers. Okay. So then the controller then communicate with the actual device. Okay. Now, typically, if you actually want to add any I/O device, so for example, one of the important devices is network card, right? So the network card, now it's probably you don't have a dedicated network card. It's basically embedded into the motherboard. But the network card is a hardware. But then there's a network card card controller. Also the controller connect to it. Okay. So then when you purchase any device, okay, and install the device in the computer system, so you can actually install the device, for example, like a PC. They provide a PCI slot, so you can insert like a. So if you want to actually put a more powerful graphics card, then you can purchase the graphics card, into the slot, PCI slot, express slot, and then you connect your monitor to the graphic card. So that's a kind of control for the monitor. Okay. Now, if you want to do this, so every time when you purchase a computer I/O devices, so typically the manufacturer going to provide the device driver. The device driver is the piece of software that used to communicate with the device controller. This device driver, which is provided by the vendor of the I/O device, communicates to the controller, device controller, through the registers. Okay, through all these registers. Okay, the inter that so these registers actually are between the driver and the controller. Okay, so these registers stores the data. For example, if you, for the import device, for the import device, if you want to actually import data from the import device, then first actually you would run the application like a Microsoft Word. You open a Microsoft Word, and then you want to, import any data, right? So you're gonna actually type the data. So the import device you're gonna use is the keyboard, right? So you use a keyboard to import the data, and so basically the, the driver basically gonna check whether the device is actually open. So if the device is ready, and they check something called a flag. If the flag it says um, it's a flag called a busy flag. If the busy flag says false, that means I'm not busy, and then the the operating system, the program and process, the program gonna actually trigger the device driver. Device driver gonna put some data into the register, and then the, the controller. Once the controller see the data in the registers, they say, okay, the controller they feel out, okay, looks like someone want to use the device. Okay, so the controller gonna read the device information and set the flag, the busy flag to true. That means I'm busy now, so I'm gonna do that thing. So the information in the register basically gave the actual instructions to the controller. Say, what do you need to do? And the controller gonna follow these instructions in the register, and typically you're gonna put the data into the buffer, into the buffer. Okay, and then once the buffer is filled, and then the 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 controller gonna actually set the busy busy flag to false. That means I'm not busy now, so you can do the next. Okay, so then the driver gonna start to read the data, get the data, and copy the data from the buffer into the memory. So this is how you're gonna import data. So let's actually talk about each of the things. Now, so the device driver is a device-specific program. So typically provided by the vendor of the device. If you buy any device, sometimes they're gonna actually give you a CD. So once you install the device, the computer may not be able to recognize the device, but you have to install the driver so then the computer can recognize the device. Okay. So it's a device-specific program that implements I/O operations requested by the user application. So when you use when you install some I/O device and the user want to use this I/O device, the user gonna trigger the driver. Okay. So the driver basically communicate with device controller. So this is how things gonna work. Now, so to be able to incorporate the new devices into the system without modification of the operating system, the operating system also support a small set of generic API instructions. Okay, based on the type of import devices. Now, why you want to you want to specify different type of device. Some of the device they call the block-oriented devices, and some of the device they called character-oriented devices. Okay, so like a disk, hard disk. If you store the file in the hard disk, these files are basically stored into each of the blocks. So when this kind of device is called block-oriented devices. So when you read the data from the hard disk, The data can be read block by block, block by block. But if you read the data from the keyboard, it's character by character, right? If you type the keyboard, it's character by character. Or if you use the like a camera or the medium players, so it's like a digital data. You basically read it actually byte by byte. Okay. And also there's another type of device called network devices. Now, the reason we want to talk about these different devices because they are different. Okay. They're different from various different perspectives. Since the device vary greatly in speed, latency, and the size of the data being transmitted. Okay. Now, typically, the speed for the character-oriented device is going to be slow. Okay. You type the key, you use the keyboard, you type the characters. You type. No matter how fast you're going to type, it's slow. Okay. You can say, I'm actually fast typer. I can type like, I don't know how much character you can type in a minute. I think that was some kind of a skills when people hire a secretary in the past, right? When they hire a secretary, the only skills they need to use is how fast you can type using typewriter. You just type, okay? Now, how fast is that? Some good typewriter, they can type the character, so they don't have to look at the keyboard. So basically, they look at the text and they just keep look at and their fingers can automatically point to the right keypad, right? So they can type very fast. How fast is that? I'm not. I can if I can type like 60 characters, actually, I'm very happy. So basically, I can type basically one character per second. But some of the typewriter, they can type like a couple of hundred characters per second. Oh, no, per minute. But it's still slow, right? If you actually copy the data from your hard disk, so you talk about how many megabytes of data you're going to copy from the hard disk into the memory. So when you do the copy, sometimes the speed is like, 6 megabytes per second, or if a slower one going to be a couple of hundred kilobytes per second. Okay. It's not the fastest, but it's still much, much faster than your keyboard, right? So that's the reason why you need to actually using a different approach to deal with different devices. Okay. A network device is like a network card. They're typically, faster now. If you use a gigabit, internet, so your network actually card can actually, I think it probably read the data at the speed of, okay, what's the speed? At least a couple of megabits per second, megabit per second, right? Normally, when you measure the speed, you use megabit, not megabytes. So, depend on these different characteristics of the I/O device, there are different approaches. So this is actually the diagram. Now, if you read the Zybook, I hope you can read the Zybook. You can play with the animation. It's the participation activity. 9.1.1. Okay, it's I/O hierarchy. Okay. So I actually used one of the diagram. I take a snapshot of one diagram. Okay. So typically the device are attached to the system using hardware controller. So each device has a hardware controller. CD-ROM has a CD-ROM controller. So keyboard, you have a keyboard controller. Printer, you have a printer controller. Okay. Modem, you have a modem controller. Now the keyboard and mouse typically use a USB controller now, but that's it doesn't matter. It's just a controller. And then, so each device is provided with a driver. So the driver, typically, you actually, when you install the device, you install the driver, right? Do you remember this experience when you, if you have actually installed any of the device in your desktop, or if you have built any desktop, you should have that experience, right? So you need a driver. Okay. Have you actually built any computer system? Okay. I got no answer. So that means uh, so you, after you build, install the I/O device, you need to actually install the corresponding driver. So typically, the controller and the device itself are basically connected. They're not really separated. So it's basically it's just a small chip in the device. But before you connect the device, you're gonna first go through that chip. That's the controller. Okay. So you have a device driver, and once you install the device, every time when you actually start your computer system, when you start to load the operating system, all the device driver are going to be loaded, because because of the device driver, the computer operating system can recognize each of the device. Okay. Otherwise, if you have no device, then it doesn't matter how you connect the device with the computer, physically connect the device with the computer. But if you don't have a driver, the operating system cannot recognize it. That's reality. So you have to have a driver and also load it, Okay. Now, so the interface between driver and the controller is basically, we call this the boundary between software and hardware. Software and hardware, that's a boundary. Okay, that basically separate your hardware with your software. So the driver is the frontline software that deal with the device controller. And the device controller is a frontline hardware that deal with the software. And then on the back of the device controller, it's the actual device. Okay, so that's the kind of configuration. So to allow the, to permit the easy addition of a new device, modern computer systems allow you to add more devices. They have actually reserved some space, like a PCI, space, so type of PCI, so you can actually insert additional hard disk into the, or hard device, any kind of physical device into the computer system. Okay, so they actually, to permit the easy addition of a new device, the I/O system, the operating system, import-output system, supports several generic API instructions. Okay, one is the read and write block, read and write character, and the send and receive data. So depending on which type of device you're going to install, and it's going to be dealt with by different operating system API instructions, generic API instructions. Okay, so a driver then basically translate each of the generic I/O instruction into corresponding device-specific operation. So when the when the manufacturer sell you the hard disk, sell you the printer, so you attach the printer using the, also most of the printer also use the USB. So when they attach the printer to the device, okay, so you install the actual driver. So once you install the driver, then the printer driver is going to provide an interface. It's called API, application interface. So when you try to use the computer for any software, use the computer, you need to call the interface provided by the device driver, and the device driver actually receive the interface call. They actually going to actually communicate with the controller, and then the controller going to communicate with the actual printer. Okay, so you don't actually twist the actual I/O device to do the job. You basically call the interface provided by the device driver, and device driver gonna actually send a command to the controller, and then controller gonna actually tell the device how to perform the job. That's basically the relationships. Okay. Okay. I'm going to stop. So next class I'm going to continue with these topics, but I think that's pretty much all we're going to talk about today. And for the next Tuesday, we can actually just finish up the I/O part. Okay. Please start the Zybook exercises. Okay, I already actually, assigned the exercises on the Zybook. Please actually do so. Okay. Now, before I wrap up, do you have any questions?
Yeah, can we talk at the end of the class?
Pardon me? What?
Can we talk after class?
Oh, if you come later, please actually read the. Did I actually record this? I recorded it, but I forgot whether I record the. So we only have actually. So I'm going to actually send, update the announcement in the Blackboard, on the Blackboard. So basically, the final exam going to be scheduled on the May 11th. Okay. So that's let's see, May 11th. That's Tuesday, May 11th. Okay.
Does the test open today at 11?
No, May 11th. No, there's no test today. I updated the, oh, okay. So I apologize that I mentioned that the syllabus, if you look at the schedule on the syllabus, you'll probably see 3 tests, but I changed that one. There's only 2 tests. So I updated the syllabus right already, so just yesterday, so to reflect the actual, schedule. So that this schedule actually, I apologize. When I put the schedule on the syllabus, it's just for reference only. That's what I mentioned earlier. So we don't have a second test, but then we have a test, we have a final exam.
Okay, thank you.
Okay. Yeah, check the Blackboard. I update the information now. So, and also, I'm going to actually send you another message in the announcement, and we're going to talk about what's the actual schedule for the last couple of classes. And the class going to actually end next week, So then, on May 6th, I think I'm not going to cover any material, but I'm still going to be available if you have any questions. So we can actually talk about it, but I'm not going to cover the topics. And the May 11th is the day that we're going to perform the test, the last test. So forget about the test, like a test 3 on the Blackboard. It's I already changed it. Okay.
Thank you, Professor. Have a good weekend.
Okay. Thank you.
I still have a question if you
Yes.
it'll be quick after class.
Okay. I think you can talk now. So everybody just left.
You're still recording.